All right, this is 13.3, fluids at rest and in motion. We're going to talk about Pascal and Bernolli's principles. We'll calculate pressure in a liquid, the buoyant force, and talk about the difference between cohesion and adhesion. First of all, cohesive forces. This is when two substances stick to each other. The same substance. Two of the same substance sticks together. So like water sticking to water, or in like macro scale, tape sticking to tape. Right? It's the same substance, the same molecule sticking to itself. This is what causes surface tension in liquids. So you can see this picture here has mercury, water, and alcohol, some sort of like rubbing alcohol. I'm not sure what this one is, but the mercury has a very strong surface tension. So it's very spherical. It likes itself. It's very selfish. And this is also what causes viscosity. So viscosity is the cohesive forces, but it's also frictional forces. So if you think of molasses, molasses is made up of lots of sugar crystals, and they're crystals, so they're kind of sharp on the ends. So as they move in the liquid, they get stuck on each other, and this is called internal friction. And that is also, along with cohesive forces, is what makes up viscosity. All right, adhesive forces. This is the attraction between two different molecules. So like tape and the table. This is what makes up the meniscus when you do a graduated cylinder. So let's look at that real quick. So here's your graduated cylinder, and here's your water. Right here where the water sticks to the side of the glass, this is an adhesive bond. This is also how plants suck up water. So there's their stem, and the water is actually sticking to the inside of the stem. So it's not that the stem is sucking the water, it's that the water is crawling up the inside of the stem through adhesive bonds. In the stems, it's called capillary action, this water crawling up the inside of the plant. So we're going to move on to Pascal's principle. It states that any pressure exerted on one part of the fluid will exert that same pressure through the whole fluid. This is used for pistons, when you have two sets of pistons. So if you have one set of piston, and it just says what's the pressure with the force in the area, pressure equals force over area for one piston. But if you have two, That was a mistake. Piston. There you go. If you have two pistons, because of Pascal's principle, the pressure in the first piston here is going to be the same as the pressure in the second piston. So if you have two pistons, they're going to have the same pressure. So pressure 1 is going to equal pressure 2. So you can replace this with force 1, area 1 equals force 2, area 2. So in this one, units don't really matter. Because if you put in centimeters cubed here, it's going to come out centimeters cubed here. But in this one, units do matter. You have to have newtons, meters squared, and pascals. So just pay attention to that. So this one would be like, this is the first piston, the force, the area. The second piston, what's the force if the area is this big. Now these areas, a lot of the times, they're going to be circles, right? Because they're circular pistons most of the time. I haven't seen a square piston before. So you're going to put a circle in there, pi r squared. If they just give you the radius of it. A lot of times they'll just give you the area, but they could just give you the radius. So you have to put it into pi r squared to find the area. That leads us to the pressure in a liquid. Pressure depends only on depth. So the deeper you go, we'll call this a well here. The deeper you go, the more water is above you. So that's the height, the depth. And the density, rho, of water is 1,000 kilograms per meters cubed. I know you're used to water being 1 for chemistry. Well, here it is 1,000 because we use SI units instead of CGS units. H is going to be your depth, and G is always 9.8. Notice it's not negative here. It's just 9.8. What's interesting is it doesn't matter if you're in the well or if you're in a huge ocean, is that the depth is really only dependent on, or your pressure is only dependent on your depth, because it's kind of like all the water right above your head crushing your depth, right? It doesn't really matter. There's pressure all the way around you, but it's about the depth that it is. So it doesn't matter if it's a well or a pool or an ocean, it's only the depth that affects you. Okay, and that leads us to buoyancy. This is the force that causes things to float. So buoyancy is dependent upon the density of the liquid that you're in, your volume, or the volume of the object. So this is the liquid, this is the object. This is not the density of the object, it's the density of the liquid you're in, and then the volume that you're displacing in that water, and then gravity. That'll mess you up a lot. A lot of times they'll give you the density of whatever the object is instead of the liquid. Now remember, for water, it's 1,000. So most of the time, this equation is going to be 1,000. So make sure you write that down, star it. It's going to be important later. We draw just a quick free body diagram of this. Here's a box. You'll have it in some sort of liquid. Let's call this, our little liquid here. This is water. It's going to have some sort of weight and some sort of buoyant force on it. So if we look at the net force equals MA, you're going to have weight down, buoyant force up. This is why when you're lifting things in water, they feel lighter. It's because this buoyant force is pushing up on it. And so it doesn't quite feel the full weight, the normal mg that we would actually calculate. You can actually have a buoyant force for air using the same equation. The only difference is that air is going to be 1, right? It's going to be much smaller. It's not really going to feel like it. You could do it for, a helium balloon, the volume of a helium balloon, and then the density of air, and you can see that it'll actually rise. So anything with a density of less than 1,000 kilograms per meters cubed is going to sink in water, and anything that is higher than 1,000 is going to float. Sorry. Anything higher than is going to sink, anything less than it is going to float. And if you take Saturn, it has a smaller density, so Saturn, if you had a huge ocean, would actually float. Of course, Saturn's really big. So if you look at the side here, if you have a large buoyant force and a small weight, it's going to float. So like an ice cube is going to float. Down here you have like a lead cube. Its weight is going to be greater than its buoyant force, so it's going to sink. And then you have this soda can somewhere in the middle here. It's got an equal buoyant force to weight force. This is what we call neutrally buoyant. Now, according to your book, when things are neutrally buoyant, they're going to bob kind of at the surface. They're going to kind of just go here. Actually, it's probably more like this, just kind of barely sticking out of the water, kind of in between. Now, there is a couple experiments you can do with, I guess, eggs or something, where they actually do float somewhere in here. But according to your book, they won't. They'll either sink, or they'll float, or they'll like super float, where they're like practically sticking out of the water like styrofoam. It's like barely touching the water. It's pushed so far up because it's taking up a lot of space, but it's not weighing a lot. So you're never going to have something in the middle. It'll either be neutrally buoyant, floating, it can float somewhere between barely floating and really floating, or it'll sink. It's not going to just hover in the middle of the water. Now, there are some exceptions to that rule, but according to your book, that's not going to happen. And I just want to point that out because it's a homework question. Okay. And the last little thing that I'm going to cover here is Bernolli's principle. And this has to do with things that flow through a pipe. Now, this actually works for traffic, too. If you think about traffic, whenever you have two lanes merging into one, like this right here, things get backed up, right? Everybody back here is waiting for these to go through. But as soon as it goes through here, like as soon as these two things merge together, you go really fast. So it's saying that the larger area, the slower it's going to go. And then the skinnier, or the less area that it's going through, the faster it's going to go. And since it's all backed up here, you're going to have a high pressure. And since it's moving fast through here, you're going to have a low pressure. So smaller area, faster velocity, lower pressure. Bigger area, slower velocity, high pressure. Think about traffic. The more cars around you, the higher the pressure is to get through, and the angrier people get. But as soon as you guys merge, like as soon as it goes into that one lane, all of a sudden you're going really fast. No more pressure. All right, I have a practice for us. We're going to do a buoyant force practice. It says, what is the tension of a cable that's attached to a 4,380 Newton crate that's fully submerged in the water? It gives us the density of the crate to be 1255 kilograms meters cubed. And we have to remember that our density is going to be mass over volume. That's going to help us at some point today. What's this 4380? It's in newtons. It's a force. What is it? The force of? Nope. Nope. It's of the crate. Right? The crate. So it's the weight of the crate. What's the what do we use when it's the weight? If it's not the mass, it's the weight. What is it? Nope. When I say weight, what equation do you think of? Mass. Close. That's not an equation. Oh. Okay. It's mass is in there though. Gravity. Mass times gravity. There we go. Mass. So mg. It's going to be mg. The weight of the crate. I know it's been a while since we used this stuff, but it's really important that you put mg there because it'll make sense in a little bit. Okay, and then we have the 1255, the 1255. What's that? The density. And it's specific. It says of the crate. So be careful because I told you that when it's the density of the object, not as helpful. Right? We want the density of the liquid. Now we're going to draw the picture. We have some crate hanging in the water, and it's just sitting there. It's not moving. It's hanging. What are the three? There are three forces acting on this crate. The buoyant force, good. The tension and gravity, mg. Figure mg again. And this is tension. So we're going to draw a free body diagram. Net force equals ma. The tension up, the buoyant force up, and the weight down. Now, is it accelerating up or down? It says it's hanging there. So this is going to be mass times 0. So this side disappears. So our tension is going to be equal to our weight minus our buoyant force, which makes sense because we're going to feel some weight, but this buoyant force is making it a little bit lighter. Now what's nice is that this is of the crate, right? Mass of the crate minus our buoyant force, which is rho of the liquid, volume of the crate, I almost put a box there, and G. So I just replaced the buoyant force with that equation that I gave you for buoyant force. Now it's important that you're looking at crate, liquid. What's the rho of the liquid? What's the density of the liquid? Do you remember? Say it louder. I can't hear. 1,000. Okay, so the density of the water, or the liquid, is 1,000. So right now we know this is right here. So this is going to be 4380 minus our density of our liquid. We don't know V, and we go 9.8. So we need to figure out what this volume is in order to figure out what tension is. Any possible hints that you might have there?
P equals M over V.
Good. Rho, density is mass over volume. Okay, volume, we have the density because, right, we're looking for the crate, so all this stuff is for the crate. We have the density of the crate to be 1255. And we're looking for the volume of the crate. How do we figure this out? Divided by 9.8. Good. Okay, so we're going to take this one, which is just mg equals 4380. We know that g is 9.8, so we'll divide 4380 divided by 9.8. So this would be 447. So our mass is 447. So you kind of have to, in order to solve this particular question, you've got to break it down into density, and then you still have to find your mass. So you've got to pull from this. This is like the hardest type of question you're going to get, so don't worry too much. So we're going to pop this mass in here, 447. Flip-flop the bottom and the top. And we'll get a volume of 0.356, and this is meters cubed. This can now go here, and we're going to go 0.356. I missed the number I saw yet. And now we can solve. So our tension is 891, and that's newtons. And now we're able to answer the question. Right. Any questions on this? This is, again, the hardest type of problem that you could possibly get. I have 4 clicker questions for you today. You guys ready? All right. Question 1. As diagrammed, an operator applies a force of 200 newtons to the first piston of hydraulic lift, which has an area of 5.4 centimeters squared. What is the pressure applied to hydraulic lift? Now this is a single piston, so you're going to use that single piston equation. Don't worry about the second piston, it doesn't say anything about it. So we have pressure equals force over area. Now remember, when you have the single piston, all your units need to be in SI units. So that one is weird. That one's not right. How do we change that?
Meters.
Into meters. Good. Okay, so how many centimeters are in a meter?
2. Negative. I don't know.
100. That's what she meant. She meant to the 2. Yeah, 10 to the 2. In 1 meter. Now what's different?
Squared.
It's squared. So all you have to do, which they probably didn't teach you that in chemistry, is square it. So that's how how you're going to convert. And then when you get the answer, you can plug it in here, and it gives you force. So you should be able to get the correct answer. And I haven't started it yet, so don't try to answer your question. All right, there you go. Now you can answer.